Now, the overall step for the fitting. So what I mean by fitting is simply this. The theory, okay, those theorems, they tell us that if we have data, exceedances should over a high threshold should approximately be GPD. So by fitting, I just mean pick a threshold, grab all the observations that are above this threshold or the exceedances, fit a GPD to it, and assess if the fit is good. And once you have a model, then you can use the model to make some sort of predictions. Now, let's go step by step. So in summary, what we're doing is, okay, we assume a sample comes from a certain distribution, any distribution. Okay, big F. Because of the theorem we just saw, if we chose appropriately a high threshold, then it's reasonable to model the distribution of exceedances, which we call F little u, by a 2-parameter GPD. Now, for the purpose of fitting, we're going to call n little u the number of x's which exceed this high threshold little u. Okay, so you might label those then x1 tilde, x2 tilde, blah, 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 up to xnu tilde. Of course, it's n little u, big N little u depends on u. Well, yes, because if you pick a very, very high threshold, then you're gonna have fewer observations that exceed this threshold. So the number of observations depends on u. Now we're going to define the excesses, because remember, it's the excesses over the threshold, so that are modeled as a GPD. So this would be x tilde j, j is just whatever observation, the index of the observation, minus u, and then we call this big W j. Big W is a notation that we've used often to mean exactly this, the exceedances over a high threshold. And so again, if u is high enough, those W should approximately, via the theorem, have a 2-parameter GPD distribution. Okay, and so then we can fit this sample, okay, the W's, the exceedances, we can fit those exceedances to a 2-parameter GPD, and then use our model. Okay, and we can do that, of course, by maximum likelihood, and then we would obtain then what you might call sigma hat and c hat, the estimates based on maximum likelihood of the 2 parameters we need for the fitting. Remember, we don't need to estimate mu because we're under the 2-parameter GPD. Mu is 0. This is all in theory. This is all in theory. Of course, this is an asymptotic result. What's the name of the theorem? Pickman's Balkema Dehaene. Balkema Dehaene. It's a theoretical result. It doesn't tell you which u to pick in practice, because it just says if u becomes incredibly large. So if you want to do fitting in practice, you need to pick some threshold. So as a general comment, if u is set too low, then maybe the fit will not be good. Well, simply because the theorem doesn't really apply, you've picked a u that's too low. Now, but you can have the opposite problem. If u is too high, well, then your estimates might be very, very variable. They'll have a very large standard error, simply because you have few data points to do the fit, because you've picked the threshold too high that there's only a few points above it. So there's some sort of trade-off there to pick a u high enough that the theorem applies relatively well, but not so high that you don't have any data to do the fitting. And here there's a bit of exploration, okay, and data exploration to choose an appropriate threshold. Maybe there's an analogy to draw with the central limit theorem here, which, remember, central limit theorem tells you the average of a sample is asymptotically normal, but how big the sample needs to be for the theorem to work relatively well, it's a bit arbitrary, and there's no single rule that tells you which sample size makes the theorem work. It actually strongly depends on the underlying distribution you have, and this is the same thing here. Different underlying distribution might need a higher or lower threshold for the theorem to apply relatively well. But again, we're going to illustrate this in a different video. If now, okay, let's just present overall what are some approaches to help us pick this threshold u. First one is very simple, but I would say it might not always really work, but still it might. Okay, so approach one is very simple. Find an initial threshold U not too high. Maybe the here just it's a bit arbitrary, but maybe the 90th percentile of the data. Then you're just going to fit with maximum likelihood your data to the model. Okay, you're going to obtain a sigma hat and a xc hat for this specific U, but repeat this by slowly increasing U. Okay, so repeat the fitting process for increasing values of U. So you get a whole series of fitted parameters, sigma hat, xc hat, for different U's. And the method is simply this. If estimated values of xc appear relatively, okay, and I stress this word relatively stable starting from a certain U, then this U can be chosen as a threshold. And why is that? It's because, if you recall the theorem, xc here, it doesn't vary, okay? It doesn't change based on how, on the value of U. This is contrary to sigma, okay? So sigma U here, this sigma U does vary depending on how U is, but xc is the same. So at a certain point, xc should become stable when you do the fitting for a higher and higher U. So at this point where you see that xc is stable, you can pick the initial U that after which xc seems to be stable in your estimates. Okay. Again, this is in theory. Maybe in practice you'll see that the xc are actually kind of variable. But if you do see that they become stable after a certain threshold, you can pick that as a threshold U. Okay, the second approach, again, those are rule of thumbs. They might not work perfectly well, but they might help us to find a U. But then after we've picked the U, probably the work doesn't stop there. You would check with usual diagnosis tools like the QQ plot or a CDF comparison that your model is actually good. So I'm just saying here, it's a rule of thumb. The second approach to pick this U is visual, and it's going to rely on what we said earlier, that this mean excess function EU is a linear function of U. And the method is this. Well, first note that from a sample, EU is straightforward to estimate, because EU, remember, it's just the average of the exceedances over U. So to estimate EU in practice for different levels, for different U's, you can do this easily. Here we call the empirical version of EU, we're going to call it E little n of U. So EU is the theoretical and EN is our empirical estimate of it. Like we have EX is the theoretical expectation and X bar is our empirical estimate of it. How do you find it? Well, simply this. It's an average. So it's the average of all the exceedances over a certain threshold. So simply do that. Take the average. So take all the xi minus u, sum them, and divide by how many of those xi do you have. And this is what this formula is doing. Yes, because here, I think you know this notation here, it's the indicator function. Okay, so this would be 1 if this thing is verified. So this is equal to 1 if xi exceeds u. So here, you're basically just summing all the exceedances over a certain u, because for all the x's that are smaller than u, this thing would be 0. So you would not be summing this exceedance. So you're summing all the exceedances over a certain threshold u, and then you divide by how many exceedances you have. So how many observations you have of x above u. Okay, this is the number of xi's or u. Well, yes, because again, indicator xi bigger than u, this would be 1 for every single observation that is bigger than u. So you're counting how many of those you have. So it's simply easy estimates of this mean for all exceedances over u. So, but now that we have this, we can construct what I said, a visual help, which is you can call this the mean excess plot. So the mean excess plot plots simply on the x-axis all the order statistics. Okay, so you remember this notation: x parenthesis I is simply x1 is the smallest observation in your data set, x2 is the second smallest, and so on. Xn would be the biggest. So you plot on the x-axis this versus the mean excess evaluated at this. So basically, let me show you just an example with real data here. For different threshold, but the threshold we just set all the order statistics to be our threshold. You plot the mean excess plot. So recall, this is just the mean of all exceedances over whatever threshold you plug into the function. Okay, and here this is an example with some real data. You see it's pretty linear, increasing the whole way through. But now, why can this help us pick U? It's because of the fact we said before. EU under the theory for a GPD is a linear function, either increasing or decreasing or flat. It's a linear function of U. But we also have the main theorem that tells us for any distribution above a high threshold, the exceedances are approximately GPD. So we use this plot and we check, can we find a U? Okay, can we find a value on the x-axis? Can we find a value on the x-axis such that from this value and upwards, the trend is linear? Yes, because the theory tells us that for a certain U, it should be that after that U, the data or the exceedance data is GPD. And for the GPD, the trend is linear. So it makes sense to pick a U such that after this U, in the data, we see a linear trend. Hope this makes a bit of sense. Now, in this example, to be honest with you, it seems quite linear the whole way through. So it's not only after high threshold that this is linear. It seems linear the whole way through. However, if we needed to pick a threshold here, we would look carefully and we would see here it's pretty linear. However, it seems that it's kind of flat. It's a bit flat here. Okay, there's a flattening out of the initial trend, which seems to be linear, and then after that, it seems to shoot upwards linearly, consistently. So here, although it's a bit arbitrary, not fully arbitrary, but there's a bit of interpretation to be done. It seems that 10 or around a value around here, so it's around 10, or maybe a bit. I would pick it maybe a slightly bigger, but anyway, around here, then you have a nice linear trend the whole way through. So it could be a good candidate here. A value around 10 would be a good candidate. And it's also a pretty high threshold because I tell you, but I'll show in the R section, 10 is actually close, I think, to the 95th quantile or percentile of the data. So it's actually a relatively high threshold. But that's the method, okay? Simply plot the mean excess plot, see if there's a linear trend after a certain threshold, and this threshold can then be picked to be U, because the theory tells you for a GPD, EU should be linear. I hope this makes a bit of sense. I think this slide is simply just saying what I said. If you see an upward trend starting from a certain U, upward trend indicates a positive Xi. Well, yes, because recall what we had over there was that it's a linear function, but the slope of this function is Xi. So if the trend is upwards, then it means Xi is positive. Likewise, if the trend is downwards, then it indicates a negative Xi. And if there's no upwards or downward trend, if this plot was something like just points like this, okay, it's not upward, like meaning if you fit a line to be a line like this, then you have some evidence that the Xi is around 0. Yeah, now here there's some words of wisdom from the book I'm using as a main reference. Let me just read it. In practice, some experience is required to read mean excess plots. Even for data that are genuinely generalized Pareto distributed, the sample mean excess plot is seldom perfectly linear, particularly towards the right-hand hand, where we are averaging a small number of large excesses. In fact, we often omit the final few points from consideration, as they can severely distort the picture. So, and yes, that makes sense, because you see here, once we get towards the last or the biggest order statistics, you see you're taking the average of only a few data points. So this estimate would be very, very variable. It's not robust at all. So in practice, you often omit those last few points from the plot. And in fact, I didn't say it, but here, the last two values are removed because the last two, they actually don't fit this trend. I think they were like much lower, but it makes sense to exclude those because again, they're based, it's an average, but only based on 2 data points. So it doesn't mean that much, you see. And again, we're going to come back to this in R and show a few more examples. Okay, 2 more slides. As we said, those are rule of thumbs to help us choose U, but they cannot just be followed blindly and then work is done, we go home. Once you've picked a U, you probably need to assess that the fit is actually decent. So, and this is, I think you know how to do this. You use the diagnosis, like you would check that the fitted CDF, the CDF of the generalized Pareto you fitted via maximum likelihood looks similar to the empirical CDF. You know, we've done this in R in previous lectures. You plot the two on the same plot and you see if there's lots of discrepancies. Of course, you can run statistical tests. You can run, I would suggest you run the Kolmogorov-Smirnov test to see if the data conforms to the fitted distribution. You can do a QQ plot. I think I'm going to present this in the R video, just to remind you what QQ plot is. If you're motivated, you can apply some of those statistical criterion like the BIC and AIC. If you have many models that are a candidate, maybe you fit it for a few different U's that you think are reasonable. Maybe you want to pick the one that has the best BIC. So yeah, those are examples of the things you can do to assess that your fit is good. Okay, and you can do what we call stress tests. So do everything again, but you remove the largest values and see if the fitting yields you similar values. Because of course the largest values are the more, let's say the more extreme, of course. So the more likely to influence your model. But if you remove 1 or 2 of the biggest data points and your fit is still the same, meaning it yields a similar Xi, then it's a good sign. It's a good sign. Okay, and one last slide. Is to highlight that how would you use your model? You need to be just a bit careful because now, remember, you have a model for exceedance data. Okay, so you have a model for what we call W there, the exceedance of X over U, but of course for only the data points that have exceeded U. Okay, so this thing here is always positive because you take only the data points that exceed a certain U. But now, so the point is this: you have a distribution. Sorry, you have a model for the distribution F little u. You don't have a model for the distribution big F, but you can use this to make prediction about F. What do I mean by that? Well, let's just review the slide. If you have a sample that comes from F, and assume you've done your work, you've picked a U, you've done some goodness of fit tests, and it seems that the U is reasonable. So you're satisfied with the fit. Now, call H hat, okay, just to mean this is the fitted distribution to exceedances, meaning is the GPD that you fitted to your exceedance data. So this is the fitted model for F little u. But you can express your F as a function of this F little u for any high threshold or high X. What do I mean by that? Well, this is just a bit of conditional probability. For any X that exceeds little u, Fx, the initial distribution of your data, can be expressed like this. Well, F little x is the probability to be smaller than X, of course. So this is a probability to be smaller than u, because here we have an X that's bigger than u, plus the probability that it's between u and X. Okay, so this would be the probability that X exceeds u times the probability that X is smaller than little x, given it has exceeded u. Okay, meaning maybe I can draw this. We just mean here the probability that here we have X that's bigger than u. So the probability that the random variable X, big X, is smaller than X is a probability to be here, which is the probability that X is smaller than u, or plus the probability to be to be over there. Okay, between U and X, which is this bit here. Well, yes, because the probability that X, it does exceed U, but then given it has exceeded U, it doesn't exceed X, so it's smaller than X given it has exceeded U. Okay, and then you can rewrite this because you want to make appear what you have, which is F little U. Here you just rewrite minus U on both sides. The probability that X minus U is smaller than little x minus little U. And why you write it this way? Because this is exactly a conditional probability that gives you big FU. Well, yes, it's a probability that the exceedance random variable X minus little U given X is bigger than U, probability that this is smaller than whatever amount. Let me find a different color. XU. Okay, so this probability is exactly F little U evaluated at whatever this argument is, X minus little U. Okay, this is what we wanted. We have Fx for big X, X that exceeds the threshold U, expressed as, well, Fu, 1 minus Fu, and then expressed as F little U. And again, I want F little U because this is what I fitted. So bottom line is this: if you want to estimate estimate the probability to be smaller than X for X a high value, but of course you can also find the probability that the probability that you are above this threshold by taking 1 minus Fx, you estimate it in the following manner. Okay, this is an estimate, so it's F, you can call it F hat. You replace Fu by Fnu. This is the empirical CDF. This is the empirical CDF. And you replace, and it's here as well, 1 minus Fu. You replace Fu by the empirical CDF of your data. And then you replace Fu by your model because you fit it. You fitted exceedance data to the GPD. So you replace F little U by H hat, because H hat is exactly as this, a model for the exceedance data over U. And so here, in essence, you have a model that can make predictions about the probability to be smaller or bigger than any high threshold, and the prediction is based on the fitted GPD. Now it's also based here on the data on the empirical CDF, but this is in essence saying up to the point U we trust the data, because up to the point U we use the empirical CDF. But then for data that is very large or higher than the threshold U, we don't trust the data. We use instead our fitted GPD, because the theory tells us for high U, the GPD should be a good model. So maybe it's slightly complex because yes, we use both the empirical CDF in calculating this, the estimate of F hat at a certain large value X. We use both the empirical CDF and our fitted model. Okay, now here I recognize there's a slight incoherence in the notation. There's a tilde here, there's no tilde here, but let me add the tilde here. Okay, F tilde N. Well, before we call this just Fn, so maybe it's better to just remove the tilde here, but you see what I mean. It's the empirical CDF of the data. Okay, I recognize it's a bit theoretical. In the tutorials, there's going to be examples about this to apply what we mean by using the model. And then in a R lecture, I'm going to try to bring those concepts a bit more to life with plots and fitting and so on. Okay, but for now, it's the bottom of the slide, so I'm going to stop here. Thanks a lot for watching, but do watch the other R videos. They should help understanding. Okay, and if you understand everything already, well, wonderful. Okay, but for now, I'll stop here. I'll catch you later.